Okay, let's get into a little bit of math. We're going to talk about the equations that engineers use to minimize weight and design something that's stiffness limited. In other words, a B-pillar that doesn't come crushing in on you. So we have equations that describe the stiffness of a beam. If you teach physics, you're familiar with the concept of a spring constant. So we're using that same idea. So in this case, if you think about going out on a diving board, and I'm afraid of heights, so this one really resonated with me. The further you walk out on the diving board, the lower that board sags and the more iffy you get. So the equation that describes this for a simply supported beam, something that's connected to a support on the left end, and the right end is free to deflect up and down, depending on the force applied, is described by this formula. So the proportional relationship between the force applied and how much my beam sags is given by two different kinds of variables. The material that I use to construct the beam shows up in the equation in the form of this big capital letter E. That is called a Young's modulus or an elastic modulus. And it's actually related back to the bond strength and the relationship between the forces connecting two atoms and how that force varies as I pull the atoms further and further apart. So you can think as my top surface of my diving board goes down, those atoms on the top surface are being pulled apart. And there's a certain resistance to that. And that's given by the bond energy versus distance curve. And the slope of that curve is directly related to our elastic modulus of our material. These variables over here in green describe the effects of the shape of the beam on the deflection. So we have something that's denoted by the capital letter I. That's called an area moment of inertia. And that is going to bring in the effects of the width and the thickness of the beam. And then we have the unsupported length of the beam, our capital letter L. So if you had a wooden stick handy, a paint stir stick works well for this, the wooden coffee stirrers from coffee houses, or even a wood ruler would work. We're going to do a quick experiment. So hold your wooden beam, and if you don't have one handy, do this as a thought experiment with us. Hold your wooden beam in the position like the diving board. Okay, that's given here in figure 1. Put your thumbs toward the center of the beam and just get a sense, without breaking it, of how much force it takes to flex your beam. Okay. Once you've got a good idea of that force, rotate your beam 90 degrees so it looks like figure 2 down here. You're going to put your thumbs in the center of the skinny edge now and try to flex it. What you'll probably observe is that it's much more difficult to flex it in that 90-degree rotated, or I call it the stiffness orientation, compared to diving board orientation. So here's the math that describes what you just felt. Okay, here's our diving board. So this term in our equation, this big capital letter I, our area moment of inertia, is given by this formula here. So the stiffness of the beam is going to be related to the width of the beam times the height cubed. Okay? So in the case where we have our diving board orientation, B, the width of the beam is larger than my height. So that skinniness of the beam in the thickness direction makes a big difference in this spring constant. Okay? If I flip my beam 90 degrees to go to what I was calling stiffness orientation, now the big number in my dimensions is cubed. So my force required to deflect the beam a certain amount goes up rapidly as I flip from diving board to stiffness orientation. So let's do a quick exercise. If I wanted to limit the deflection of the beam to less than or equal to 1 centimeter, that's this Y here, from my original position to my final position, how much mass would it take to do that if my beam is oriented as a 2x6 in diving board orientation or as a 6x2 in stiffness orientation? And I'm going to assume that I have a 1 meter unsupported length of my beam, because that makes the math easier. And I'm going to assume that it's made out of red pine. Red pine happens to have an inherent material stiffness, our modulus, of about 10 to the 10 newtons per meter squared. And if you're a physics person, you'll recognize that as a force per square area, or force per area unit. So that's like pressure. In engineering, we would call that a stress unit. Okay? So if I rearrange this equation, I do a little bit of algebra, I can come up with my force required to deflect this by 1 centimeter, okay, is proportional to this equation I. That was our BH cubed formula. So I'm just going to make a quick little spreadsheet, and I'm going to plug in my 6 centimeters wide by 2 centimeters high, my diving board orientation, and my stiffness orientation. So that's all I'm doing here is changing the numbers that go into I. And it turns out that the force required to deflect this beam as I go from diving board to stiff orientation goes up by about a factor of 9. Okay, if I work this same problem and I say, suppose I had to support 100 kilograms, how far is that beam going to deflect? Okay, we do the same kind of algebra, we're just solving for y, for my deflection, instead of for F, my force, in this case. So using that same little spreadsheet, here's my diving board orientation. To support that same 100 kilogram, I think that was 100 kilograms, yep, mass, my diving board orientation is going to deflect roughly 9 times greater than my stiff orientation. Okay. So if I look at the effect of the kind of material I choose to make my beam, that shows up in our equation in the form of this elastic modulus, capital E. So if you look around at I-beams, most of those are made out of steel, and that has a stiffness of about 200 gigapascals. Okay. Concrete is a quarter as stiff or worse. Okay. So our highway bridges are actually not so stiff if you took the steel out of them. Wood, we mentioned pine, runs around 11. So that's like 5% of steel. And if you use something like the polymer wood composites, one of the brand names is Trex for decking. Say I was making a park bench and I wanted to make it out of wood, or maybe I like the Trex because then I don't have to worry about the sanding and staining all the time. The Trex is going to be twice as flexible, half as stiff as the pine. Okay, so how does that affect us? You don't want to sit down on a park bench style bench and have the slats flex very far, because that's going to feel very unstable to you. So, and we also want to be able to move our bench around. My husband and I bought a new patio set last year, and one of the problems that we wanted to solve was our wood chairs kept getting blown off the patio. So we wanted something much heavier that the wood wouldn't blow. So we ended up using a plastic or polymer and wood composite chair, and it's worked very well, even with our storms. But let's look at how the materials compare. Now, I still want to be able to move my patio furniture, so I do care how much it weighs. So this graph looks at the modulus of elasticity, that's our big capital E, our stiffness, versus density. Okay. So to get the same amount of stiffness in my bench slats, the worst of the woods down here, these are our softwoods, our coniferae, would come in about 6,000 or so in the megapascals and the stiffness. Okay, and that's going to be associated with the density on the order of 400 kilograms per meter cubed. The best of my engineered composites, my polymer wood composites, comes in at about that same stiffness. But my density is 3 times higher. So to get the same performance, that same acceptable amount of flex when I sit down on the bench, my polymer composite is going to weigh about 3 times more than my wood. And if you're looking for a complex graph project for your students, engineers take mass into account by looking at specific properties. We call them specific. So what we've done is we've taken that big capital letter E value here for stiffness, and we've divided it by the density of the material. So this allows us to compare different kinds of materials based on the stiffness to weight ratio. Down here on the x-axis, we've taken strength data, how much force does it take to break something or to permanently deform it, and we've divided by the density. So this gives me a way to plot the behavior of a wide range of materials while I take the mass into account. So normally in a design situation, I would have a specified strength requirement that I have to meet, and I would be interested in how much movement there was associated with that force. That's like the 100-kilogram person walking out on the diagram, or on the diving board, and we're only allowed to flex 1 centimeter. Okay, or I would have an allowable amount of flex, because most of our parts are not used all by themselves. They're next to some other part, and they can only flex so much before they'll run into something and cause a failure. So in that case, I would be looking at how much force is required to stay below that deflection limit. And one of the fun things about being a materials engineer is we're constantly seeing battles between all these different material families. So we have to stay up to speed on the latest developments in a wide range of potential materials choices. Okay, I'm going to stop the video there, and we'll pick up again to talk you through